Um, welcome one, welcome all. How are you guys today? I'm glad to hear it. I hope you guys are well. I hope this does nothing to change that. It is Wednesday, our second saddest day of the week. So, and it really is recording.
Yes.
So, last time we spoke of heat, right? And we were talking about energy in transit, and the cause of the transit is a difference in temperatures, right? Of its own accord, energy flows as heat from the warmer object to the cooler object. That's okay?
Yeah.
All right. So then, I'm not going to go into this at length, but I want to speak of first order phase change. So in our usual statement of things, if you continue to add energy as heat to a solid, it will raise the temperature. But if you keep doing that, you'll get to a point where you input energy as heat, but the temperature ceases to go up. And at that point, we note that we get a phase transition. And that one is melted. Yay? If you continue to add energy to the nascent liquid, our newly formed liquid, you'll see that the temperature goes up for a while. And then again, we'll get to this point where you add energy as heat, and again you hit this plateau in temperature. And again, you're encountering a phase change, and this is from liquid to gas, and this is our vaporization. So,
Can't pressure cause phase changes as well?
absolutely. So if you take properties of engineering materials courses, I know you have. You can see phase diagrams written on a temperature axis, on a pressure axis, and we're not really going to address that very much, except to say that it's much easier to cause something to boil as you reduce the pressure, and that's actually a fun demo. And
Water boils in a vacuum, right?
so we have a small bell jar, and we can take a roughing pump and take it to a very, very low ambient pressure, and then even at room temperature, you'll see the things start to boil. I'm too lazy, old, and weak, take your pick, to carry one of our pumps down here. So instead, I'll probably do that one of the days we're upstairs.
What about mercury? Does its properties act like liquid, or is it different? Because I was trying to find that.
So at our
The middle
standard
one.
temperatures, pressures, it's a liquid. Again, you can play with the phase diagrams and try and take it to the solid region, but if you just broke open a mercury thermometer in this room,
When the
you'd
vacuum.
have some vapor, but you'd also have a puddle of liquid. So. If we do this in reverse, if we take energy out of the gas's heat, we could condense. So and removing more energy as heat would lower the temperature of the liquid that we produced. Eventually we'd get to a point where taking more energy out stopped lowering the temperature, and this would be our solidification or our freezing. Is that, at least in a qualitative sense, not so bad?
Yeah.
Okay. We can actually provide a quantitative statement about the energy added or removed as heat to go from liquid to gas or gas to liquid or solid to liquid or liquid to gas. Sorry, yeah. Well, you can go in that direction, or a liquid to solid, right? And the symbol we've been using for heat is Q, and the latent heat is the heat that has to be added or removed per gram or per mass to go from, let's say we were dealing with water or standard pressures, water at 100 degrees Celsius to steam at 100 degrees Celsius. So that would be the latent heat of vaporization. And Q, the mass of whatever liquid or mass of whatever material you're talking about, times the latent heat of fusion. Is the one that goes with this. This is the one that goes with this. Is that all right?
What's the Q and M?
Q is the energy that needs to be added as heat to go rightwards on our journey. M is the mass of whatever substance we're talking about.
And L?
L is our latent heat. So latent heat of vaporization, latent heat of fusion. So if we plotted the temperature as a function of heat input, I guess I could do this in calories. For, let's start with ice at so at 0 degrees Celsius, and let's 1 gram. The latent heat of fusion water is our 80 calories per gram, and vaporization is 540. So the first thing that we would find as we began adding energy to this is that the temperature is not changing.
Where's the energy going?
Well, so in this case, we have solid ice, and so there are bonds holding the water molecules together. And so we are giving energy to pay back the debt, essentially, to break those bonds.
Intermolecular forces.
Yeah, we're basically giving them energy to liberate themselves from their fixed location. So if this is 1 gram of ice initially at 0 degrees Celsius, how much energy do I need to add before all of the ice melts?
80.
80 calories, right? So do you guys remember what the specific heat of water is? It's 1 calorie per gram degree Celsius. Should be clear that I'm talking about the liquid. So now what happens as we add energy as heat? So kind of in my really bad block diagram here, we start out with 1 gram ice cube at 0 degrees Celsius. We add 80 calories. You guys just told me that we now have 1 gram of liquid. What's the temperature?
0 degrees.
It's also 0 Celsius, right? And so now we're going to add more energy. And what's going to happen?
Temperature is going to...
Temperature starts to increase, right? But it remains liquid. So at what point do we encounter the next, at what temperature for standard pressures are we going to encounter the next phase transition?
40. Oh.
100, yeah. And so how many calories do we need to make that happen?
540.
So we have Q
What is CH2O?
is
What
M
is CH2O?
C delta T.
Calorie of water liquid.
So what's our mass here?
1 gram.
1 gram. What's C?
1 calorie.
1 calorie per gram degree Celsius. What's delta T?
Changing temperature.
100.
So the later is the 100 degrees Celsius. The earlier, where did we start?
0.
So delta T is 100 degrees Celsius. So 1 times 1 times 100 is grams times calories per gram degree Celsius times degree Celsius. 100 calories. So where is that? Obviously not scale. How about 180? Does that work? And then now what's going to happen if we continue adding energy as heat. So now we'll start to vaporize our gram of water into steam, yeah? And so,
It's like a constant for each
so how much do I,
element.
how much do I need to add to fully vaporize this?
C doesn't cost
360.
calories per gram at a certain temperature.
Well, M times L vapor, what's the mass?
One of the main variables.
1 gram, what's L vapor? 540, so what's 1 times 540?
540.
So how much do I have to add?
540.
Okay, so 180 plus 540,
720.
720?
Yeah. We scale.
What would happen, so what's the temperature? Oh. My bad pictogram. So we added 100 calories here?
Wait, so the latent heat is how many calories you have to add for it to go from one
To change the phase. So to go from, say, liquid to gas or from solid to liquid, it's how much the gas has to give away to turn back into liquid per gram, or how much the liquid has to get expelled to turn back into solid per gram. So then we just added 540 grams or calories. And what do we get out of that?
Vapor.
I don't know if that's really still a gram. And what's the temperature?
100.
100 degrees Celsius. What happens if we start adding energy as heat to the steam?
The volume increases.
That's actually a good point. Let's assume that we were enclosing this.
Pressure increase.
There's lots of things that can change, but we can start to, what I wanted to get at is we can start to change the temperature again, right?
Oh, so if you
But you're right.
raise the temperature, you raise
I didn't
the
give you enough information to state exactly what happens in that case. We're happy enough with this. Questions, comments, concerns?
So
So-
if we go back the other way, that's the same amount of energy we'll get, right?
Yep. Yeah, so a steam burn is worse than, a steam burn at 100 degrees Celsius is worse than the same mass of water burning you at 100 degrees Celsius. Why so? Why is this 1 gram of steam on my
Doesn't it
skin
have-
at 100 degrees Celsius going to be a worse burn than 1 gram of water on my skin that was if the water was originally at 100 degrees Celsius?
Isn't it more energy?
It does. How much more energy for a gram of steam versus a gram of boiling water?
720 versus
Will be
80.
the-
An extra 540 calories that I'm going to have to absorb, right?
Yeah.
Before I can start to lower the temperature of the steam, what do I have to do? I first have to turn it into water, right? So I first have to absorb that 540 calories to turn it back into water, and then I have to take that water at 100 degrees Celsius and lower it to my skin temperature. So it's just extra energy that I have to absorb, right?
And that's why your skin starts to sizzle.
For an appreciable amount of water or steam, it's not going to be super pleasant.
Yeah.
A drop is probably not. We're okay enough with this. So, and I've forgotten,
It's 302.
thank you. And this ends at 3:55?
Yes, sir.
Yes.
So in lab tomorrow, we're going to do our calorimetry experiment, and let me briefly set this up for you guys. So we're going to take some mass M of metal. We're going to use a copper shot. Why do you think we're going to use a copper shot here instead of just a big block of copper?
More cost effective?
Not really. We bought this stuff a long time ago before people started really going into construction sites and stealing copper. But two, they're selling it to you by the mass typically. Have you ever had a drink cooled with an ice cube? I know it's a.
Yeah, of course.
Actually, not.
I'm an old man, so this is like a marvel of modern technology for me. Have you ever had a drink cooled by like crushed ice?
Yes.
Yeah. with
Which
friends.
one cools faster? The
The
crushed ice does. Why?
Surface area.
More air.
There's more surface area, right? So we're going to use metal shot here specifically because there's more surface area. It's easier for it to give away energy. Does that make sense? Kind of the reverse of putting the crushed ice into a drink. There, it's more surface area to absorb energy more readily. So we're going to take metal at some
Wait, which one is more quickly? The ice
more
cube.
surface area allows it to for the energy to transfer more rapidly. So the crushed ice has more surface area.
Oh, yeah, okay.
So we're going to take some metal initially at some high temperature. We're going to pour it into a calorimeter. Calorimeter is kind of a device for doing these sorts of experiments. And the cool thing about this is it has a cup inside a cup. And this is only loosely connected to the wall so that there's a layer of air insulation here. Why do we wear clothes? We aren't that furry, right? So modesty aside, in fact, modesty probably comes from this in some odd sense. When we're wearing clothes, we're trapping a layer of air next to our body. That rapidly is warmed to body temperature. And that provides an insulating layer between us and the environment. As it turns out, air isn't a particularly good conductor. We'll talk about heat transfer mechanisms in a second. But, that's largely the role of clothes, right? Here we have a cup inside a bigger cup. This layer of air provides kind of a blanket, if you will. There's also a lid on this thing to prevent convection or losses to convection, or at least minimize losses to convection. We'll talk about that again in a second. But there is some known mass of water at some cold temperature. There is also the cup holding the water, which is also going to be at T cold. Because they're in thermal contact, they achieve thermal equilibrium. The setup here is sort of okay. So we know the temperature, we know the mass, we know the temperature, we know the mass, we know the temperature, we know the mass, and then we're gonna mix them together. So we'll rapidly put the hot metal into the calorimeter cup containing the water, and we'll record the ultimate equilibrium temperature. So this is before. The after is, I can't draw the same picture twice to save my life.
Copy and paste.
And then it will be at some equilibrium temperature. Yay? So let's turn to this equation. And if heat is just the energy in transit, right? And at this point in your physics careers, you have drunk the Kool-Aid and you believe in conservation of energy. Yay? Okay. Then we could say that the energies have to balance here, right? We could say that Q for the metal plus Q for the water plus Q for the cup should be 0. Yeah? If I add 3 things, how can they equal 0? Okay.
One of the keys has to be negative.
One of them is negative, and which one is it?
The metal.
At least one of them has to be negative, but not all of them.
The water?
Oh, the metal. Is it?
The metal.
Loses.
So, what is the negative sign telling me?
Losing it.
Lost heat.
It gave energy. It didn't absorb energy as heat. It gave energy as heat, right? If we think of it as having boundaries, right? It wasn't energy flowing into that boundary as heat. It was energy flowing out of that boundary as heat. Yeah? So we could say that M metal, C metal, delta T metal needs to equal, oh wait, well, yeah, I can do that. M water, C water, delta T water, plus M cup, C cup, delta T cup. Yay? And I can plug in delta, what I mean by delta T. Say that M metal times C metal times, what's T later? Delta anything is T later minus T earlier, right? So what's T later here?
T equilibrium.
Equilibrium temperature. What was T earlier for the metal? T hot. What is T later for the water?
Equilibrium.
It's also equilibrium temperature. What's T earlier for the water? T cold. What's T later for the cup?
T equilibrium.
Also T equilibrium. And T earlier?
T cold.
Also T cold. Yay? So, in lab, you'll measure the mass of the metal, you'll measure the mass of the cup, you'll measure the mass of the water, you'll use a thermometer to measure the temperature of the metal before you transferred, the temperature of the water and consequently the cup before you transferred. We know the specific heat of water is what? 1 calorie per gram degree Celsius. We will tell you what the specific heat capacity of the cup is. I think they're all aluminum, so I think that, and I think it's printed on the side of all of them anyway. But then the only thing we won't know is what?
Specific heat of copper.
The specific heat of whatever this metal is, right? And so we'll use that to measure the specific heat of the metal. So one equation, one unknown. So far, so good. That's our lab. We'll talk about this tomorrow, but it is a lot of sitting around waiting for stuff to heat up. Very little action. So it doesn't take particularly long, but if you accidentally, don't get the metal into the cup or you splash water out, that's a problem, right? Because you bothered to measure the masses. So if the lab doesn't take long the first time you do it, probably won't take long the second time you have to do it if you don't do it right the first time. Questions, comments, concerns about that? All right, so that's tomorrow. Actually, let's do it this way. Okay. So I was saying that there are 3 mechanisms by which we say we transfer energy as heat. So 3 heat transfer mechanisms. They are conduction, convection, and radiation. So conduction is the transfer of energy as heat through direct contact. So it's typically for solids. So when I when I touch my hand to the metal tray for holding our whiteboard markers, I feel cold, right? Describe what's actually happening.
The energy from your hand is transferring.
Yeah, my hand is, again, if we think of boundaries, right? Energy is transferring out of my hand as heat, and energy is transferring into the tray as heat. Yeah? So it's not cold, right? It's not the cold that's flowing from, cold doesn't flow. It's not cold flowing from the tray into my hand. What's actually happening is energy is transferring out of my hand into the tray.
It's like the electrons are only flowing.
Yeah, it's electrons flow.
So this isn't, there probably is
Properties.
without friction, right? Very, very little transfer of electrons in this case. I think that I'm pretty darn close to charge neutral at the moment. And so there probably isn't a transfer of charge in this. But
I'm just saying
there,
it's the same concept.
it's a similar idea. In fact, I think
Because it's
the other day I was saying that things that are good electrical conductors also tend to be very good thermal conductors.
Is there an equation that relates the
You
two?
mentioned that.
Not directly that I know of. There are probably some special cases where you can get a more direct relationship, but not broadly, that at least not that I know of. So there is an equation describing thermal conductance. So we could look at the time rate at which energy flows as heat. Sometimes you'll see this as Q dot. So always looking for a shorter way of writing things, right? So the limit of delta Q over delta T as delta T approaches 0, that was too long, and so what did we abbreviate that as?
Q dot.
dq dt. But dq dt, oh goodness, I'm an old man. I don't have that much time left. And so,
Pretty young brother.
Don't die.
so one way of writing out dq dt is q dot. What if it was the second derivative of q with respect to t?
Double dot.
Q double dot, right? Right, but so as you look through different books, you'll see slightly different notations for this, but oftentimes you'll see it as Q dot. So kappa, I can't write good kappas, sorry, times the cross-sectional area times, or the contact cross-sectional area. So if you have, let me see if I can draw this at all in a passable sense. So if you have two surfaces, and this surface is at T1, and the surface at the back is at T2, and cross-section of this is A, then this coefficient of thermal conduction is speaking to the rate at which energy is transferred as heat. Yay-ish?
Why do you pick that cross-section?
Is it in the middle?
Just arbitrary.
It could be the other way, it would still work.
It has to be perpendicular to the line connecting the T1 to the T2. Does that make sense?
Yeah.
So as a do you guys want this still, or should I erase it or move to the board behind it?
It's okay to erase.
Erase? Okay. In our experiment with democratic ideals in a class of 26 people, two voices, our two voters decided for all.
Let's record it.
Yeah, people at home don't get a vote. So. If you stay home, you don't vote.
You can pause it too.
True. By the way, has anyone tried it? Like, can you actually hear me and stuff?
Mike's like right there.
I know. There's two of them even. Supposedly you can even get it in stereo. Yeah.
Put on my headphones.
We spent quite a bit of time trying to figure out how to get it to stop recording in mono and start recording in stereo.
Get you surround sound in my living room.
Get them all connection going.
Dolby Atmos.
Sadly, whether it's in stereo or not, my voice is still completely monotone. So.
You can add some bass in there.
The voice is fine.
Oh, you're very kind, but I don't give extra credit.
I was looking for it, but it's not what I hear.
At least try.
Your voice is sexy.
No way.
So we're gonna take an old-timey refrigerator, a wood box, we're gonna stuff it with enough ice that we can lower the temperature inside to about 0 degrees Celsius. And then T outside is your room temperature. Maybe your porch temperature. You don't want melting ice leaking onto your inside floors. And I suppose I need to tell you that, let's see. Kappa for wood is roundabout 0.02 calories per second per meter per degree Celsius. So somewhere MC Escher is crying, but I will endeavor to draw perspective again. Good golly. All right, so